Okay, great. So welcome back. So today we're going to continue our discussion. So we've been spending a lot of time now on eigenvalues and eigenvectors and some of their implications, both for both in linear algebra and for the kinds of problems that we've been looking at. Right? We saw that eigenvalues lend themselves to giving us solutions to linear equations, and they under certain conditions, and they also can be used to define a new family of convex constraints, right? Namely that matrices have to be positive semi-definite. And we use those positive semi-definite constraints to show that, again, using eigenvectors and eigenvalues, that we can construct notion duality for these kinds of constraints. And we saw some examples of that in class. So today I want to continue that discussion in some sense and talk about the singular value decomposition. Again, if you saw this in a linear algebra class, you probably saw it at a very high level. Personally, I don't think I saw this in linear algebra. I think I saw it in a numerical analysis course. But in some ways it's just as important and just as useful as the notion of eigenvectors and eigenvalues, the notion of a singular value. They have basically very similar utility in practice. But we'll see actually that, my impression of the singular value stuff is that it comes up in certain applications, but those applications can be a little bit far removed from a typical linear algebra course content. So it might seem like you're reaching a bit at straws, and it's just kind of a random thing that's been thrown in rather than sort of a principled discussion about the thing. So we'll try to kind of go through it slowly. So what I wanted to do today was introduce the singular value decomposition, show you kind of where it comes from. Like I said, I found what I thought was a really nice argument for the derivation. So there's a lot of different ways that people will derive the singular value decomposition. There's a lot of different ways to see it. The book has sort of an argument in reverse, if you want to take a look, in their sort of linear algebra review section. But I found a nice argument online, so we're going to go through that and convince ourselves, right, about the existence of the singular value decomposition. But I want to show you that using the singular value decomposition, we can go back and look at solving linear systems again and actually present a really nice unified way to find solutions to linear systems. And the only requirement for solving the systems will then be to actually compute the singular value decomposition, so that if you can do that, you could basically solve linear systems really, really efficiently. And then we'll take a look at some other applications of eigenvectors, eigenvalues in sort of an optimization context. I wanted to do one example of at least one example, but primarily one today. I don't think we'll have time to do more than that. Of how you would use some of these concepts in an actual to solve an actual problem. Okay. All right, so let's get started. Unless there's any sort of lingering questions about eigenvectors, eigenvalues. I mean, what's the general consensus? How are people feeling about this kind of stuff? It's a little bit different from the first part of the course, so I kind of want to make sure that I checked in last time, but I'd like to check in one more time just to make sure that everyone is feeling okay, at least is able to follow along, at a high level. It's hard to ask deep homework questions about this, so the kinds of questions that we'll see are still going to involve sort of taking these ideas and applying them in an optimization context, right? But I want to make sure that we're all kind of comfortable with the decompositions and all of that. So are there any questions? Okay. Well, if anything comes up as we go along, please interrupt. Okay. So I think we talked a little bit about the motivation last time, but the idea is basically the same as what we've been doing for symmetric matrices, trying to extend that factorization to more general matrices. So recall again, that any symmetric matrix can be factorized as Q D Q transpose for some orthogonal matrix Q and some diagonal matrix D. So remember that a matrix is orthogonal if its columns and rows are orthonormal vectors, right? So in this particular case, this decomposition comes from the eigenvectors. So Q is the orthogonal matrix whose columns are the eigenvectors of the matrix A. The orthonormal, in fact, a collection of orthonormal eigenvectors for the matrix A. And D is the diagonal matrix of eigenvalues in similar order. So the first column of A corresponds to an eigenvector whose 1, 1 entry in D is the corresponding eigenvalue for that eigenvector. Okay. Again, just to emphasize, the ordering really is important. You wouldn't be constructing these matrices probably yourself because in both Python and other numerical programming packages, when you can ask for this decomposition, the numerical analysis toolkit will likely give the decomposition back to you in this form. So the question we'd like to answer first today is there a generalization of this for arbitrary matrices? And the answer is yes, and it turns out to be very, very useful in a sort of similar kinds of ways to that we saw that this QDQ transpose eigenvector or eigenvalue factorization was useful. And it's the construction is very similar to what we saw above. The only difference is now that it's not symmetric, so we can't have a decomposition of the form QDQ transpose, right? We'd have to have, because that's inherently symmetric, we'd have to have some non-symmetric decomposition. The singular value decomposition is exactly that generalization. So it applies to arbitrary matrices, not necessarily square. So if you're given an M by N matrix, the singular value decomposition factorizes that matrix A as U times sigma times V transpose, where U is an M by M matrix and V is an N by N matrix. They're both orthogonal, so just like Q is an orthogonal matrix, U and V are required to be orthogonal in the singular value decomposition. And sigma is an M by N diagonal matrix, whose diagonal entries are called the singular values of A. So again, it's weird that we use the same terminology even for non-square matrices when we talk about diagonals. So again, a matrix is diagonal if the only non-zero elements are the 1, 1, the 2, 2, the 3, 3, etc. Right? So if a matrix is not square, what that means is that there'll be some rows or columns that are equal to 0. Right? So for example, if we had a 3 by 4 matrix here, right? And if I fill in all the entries, right? Oops, that's everything 3 by 4, right? You'll notice that there's, for example, a column here of zeros. Right? But this is the extension of what we mean by diagonal. It's exactly the same definition, only now, right? There's some strange behavior that will get some 0 rows or columns depending on the shape of the matrix. So it should be almost immediately obvious from at least from the definition. This will be pretty useful in basically the same ways that the eigenvector eigenvalue decomposition was useful, right? In that it's a decomposition into orthogonal matrices and some diagonal matrix. Right? The trickier bit to see though is why something like this exists, right? So in some ways it was sort of easier to see the factorization into eigenvectors and eigenvalues. That sort of was just a natural outcome of the matrix A having n linearly independent eigenvectors. Here it's a little trickier, and the derivation involves looking at matrices beyond the matrix A. So we'll see that momentarily. Any questions though about the basic singular value decomposition, like what it is? So U, V, and sigma are orthogonal matrices, and M are U and V are orthogonal matrices, and sigma is this generalized diagonal matrix. Okay, so I'm going to make the argument that this thing always exists. So we're going to start with an arbitrary m by n matrix. And we're going to take a look at the positive semi-definite matrix A transpose A. So you remember, right, we argued that this thing is always positive semi-definite, right? We did that maybe 2 or 3 lectures ago now. Similarly, the matrix A transpose is also always positive semi-definite. We proved that's the case basically from the definition, and the same thing is true here. So for the moment, let's assume that this matrix is more than positive semi-definite. Let's assume that it's positive definite. That is, that it doesn't have any 0 eigenvalues. So we're looking at this matrix, and using our previous notation, let's assume that it's positive definite for the moment. The generalization beyond positive definite we'll come back to in a minute. It's just sort of easier to explain the construction if I make that assumption first. Okay, so because the matrix A transpose A is positive semi-definite, that means it can be written, right, as well, first of all, it's symmetric, so that it can be written as a sum over eigenvalues times its eigenvector, right? So this is just the standard eigenvector eigenvalue decomposition for the matrix A transpose A. And again, the assumption here is that these eigenvectors V are orthonormal eigenvectors in Rn. Right, so A transpose A is an n by n matrix, so it has eigenvectors in Rn. So V is in these are vectors in Rn. So we're going to define sigma to be the square root of lambda I. So typically I'll use lambda for eigenvalues, and sigma will be my notation for singular values. So sigma, as a cheat is looking ahead a little bit, is actually going to be these will be the singular values that are the diagonal entries of the matrix sigma, capital sigma, momentarily. Now the trick in all of this is to define a new collection of vectors U, such that Ui is equal to A times Vi over sigma I. So there's a couple things that we can check about this definition for U. The first is that Ui transpose Ui is equal to 1. So let's check that first. So I have a little space here. So Ui transpose is equal to Vi transpose A transpose over sigma I times A times Vi over sigma I. So by construction, right, Vi is an eigenvector of the matrix A transpose A, right? That means that A transpose A times Vi is equal to lambda I times Vi. Right, so this is just lambda I times Vi transpose Vi divided by sigma I squared. Sigma I is just the square root of lambda I, so these things cancel. And remember, all the lambda i's are greater than or equal to 0, so sigma I squared, they cancel directly, and then Vi transpose Vi is just equal to 1. I got those initial expressions just by this definition. I'm just defining some vector U to be A times Vi over sigma I, just by definition. I'm constructing it. That was a question in the chat. Does that answer the question? So I'm just looking at it as Ui transpose Ui, right, under this definition of Ui. And so it's equal to 1. So these U's are all unit length vectors. So that's the first thing. The second thing we can check is that the U's are actually eigenvectors of AA transpose. So Yes, yes. I'm just using the definition to prove the nodes. Yes, correct. So the second thing I want to show, right, is that UI is an eigenvector of AA transpose. So again, I take AA transpose, multiplied by U, which is equal to, by definition below here, is just A times VI, right, over sigma I. Oops. Sigma I. Okay. Now again, we can do the multiplication in any order we want. So kind of regrouping this thing, we have A transpose A times VI over sigma I, and all of that times A. But A transpose A times VI is just equal to A times lambda I times VI, all divided by sigma I. But sigma I is the square root of well, let's just rearrange this last term, right? So rearranging this thing, this looks like this is equal to lambda I times A times VI over sigma I, which is just equal to lambda I. Oops. Tough to write at the bottom of the slides with the pen. Lambda I times UI, just by definition. So what that tells me is that UI is an eigenvector, right, of the matrix AA transpose. So what we've got so far is we've got orthonormal eigenvectors V of A transpose A with corresponding lambda eigenvalues lambda I. What we just did was show that if you give me the eigenvectors of A transpose A, I can construct the eigenvectors of A transpose. So the UIs here are eigenvectors, unit length of AA transpose. The last thing I want to show before we move on is that they're actually they actually form the collection of orthonormal eigenvectors of AA transpose. So the final thing that I want to show here is that UI transpose UJ, when I is not equal to J, should be equal to 0. So again, let's prove that. It's just some straightforward algebra just by plugging in the definitions. Now, erase everything up here. So what I'm looking at here is to show that the UIs are orthonormal. So I take UI transpose UJ. By definition, UI transpose is equal to VI transpose A transpose all over sigma I. And UJ is equal to A times VJ all divided by sigma J. Now again, using the fact that Vj is an eigenvector of A transpose A, I get that that expression is just equal to Vi transpose Vj times lambda J, all of this divided by sigma I, sigma J. But because the VIs are the orthonormal eigenvectors of the matrix A, this expression is just equal to 0, right? Because Vi transpose Vj is equal to 0. So what we've just shown is that given the orthonormal vectors of the matrix A transpose A, we can construct orthonormal eigenvectors of the matrix AA transpose. And further, actually, what we see from this argument is that it is something slightly stronger than what we had proven before, namely that the eigenvalues of A transpose A and AA transpose are exactly the same. So these two matrices have the same eigenvalues. They differ only in their eigenvectors. Okay, now it's worth noting here, again, right, we're looking at m by n matrices, right? So the v's are in an n-dimensional space, and the u's are in an m-dimensional space, right? So the vectors are of different dimensions if the matrix A is not square. They lie in different spaces, vector spaces. Okay. Questions about this argument so far, right? So to prove these kinds of things, you just basically plug in the definition, right, and use the properties of eigenvectors and eigenvalues for the matrix A transpose A to prove the nodes I have here. Questions? One other thing to point out while you're thinking, if you have any questions, is that it was critical here, right, that all the eigenvalues were greater than 0, right? The reason for that is that I'm constructing the singular values by dividing by the, by constructing u by dividing by the singular values. So I need all the lambdas to be strictly larger than 0 if I'm going to do this. If they're not, we'll see that we can still make the same argument, but I need to sort of handle the fact that some of these cases, some of the eigenvalues could be 0. We'll come back to that. Okay, so let's complete the argument. So we just proved these three things, right? 1, 2, and 3. So we proved that the U's are orthonormal eigenvectors of A transpose. The last thing to do is just a little bit of algebra to rewrite these expressions that we've just constructed in a slightly different way. So let's define the matrix sigma to be a diagonal matrix with sigma ii, capital sigma ii, equal to little sigma I, right? So again, right, this sigma matrix is supposed to be the matrix of singular values. So its diagonal entries are just given by the little sigmas. And I'm similarly going to define sigma inverse to be a diagonal matrix with sigma ii inverse equal to 1 over sigma I. Now, strictly speaking, right, like, you know, this sigma inverse matrix is an actual inverse matrix in the sense that if I take sigma and multiply it by sigma inverse, I get the identity matrix. We can prove that in a second, but it's worth pointing out that sigma is almost essentially an orthonormal matrix, right? So certainly, you know, sigma has orthogonal columns, right? They're just not unit length. The reason they're not unit length is that the singular values, right, don't have to be equal to 1. But let's quickly prove that sigma times sigma inverse ii, you know, gives us back the identity matrix. It's going to be useful for us a bunch today, so it's worth kind of going through. I'm not going to do the argument in general. Let's just assume we again have a let's say a 3 by 4 matrix. Right, so sigma looks like this. The diagonal 3 by 4 matrix, and then sigma inverse looks the same way. So if we're going to multiply the two together, right, I have 1 over sigma 1 1 over sigma 2, and 1 over sigma 3. Something like this. So when I multiply these two things together, what I should end up with, right? I take taking a the inverse is actually the opposite direction. It's 4 by 3, so which makes sense. I need to have the matrices need to be able to multiply each other together. So 4 by 3 looks like this. Okay. So sigma inverse is a diagonal 4 by 3 matrix. So if I take a 3 by 4 matrix and multiply it by a 4 by 3 matrix, right, what I should get back is a 3 by 3 matrix. Now see what the entries in that 3 by 3 matrix are. Well, I take the first column of sigma inverse here, multiply it by the first row of sigma, and I just get 1. Right? I dot them together and I get 1 because sigma times 1 over sigma is 1, and the rest of the entries are 0. When I take this and dot it with the second row, I get 0, and the third row I get 0, right? Because they have no overlapping non-zero entries. And I get the same thing for the second column, right? So the second column of sigma inverse dotted with the first row is 0, dotted with the second row is 1, dotted with the third row is 0. Then finally, the third column of sigma inverse dotted with the first row of sigma is 0, the second row is 0, and the third row is 1. So when I dot these two, when I multiply these two matrices together, I get back the 3 by 3 identity matrix. Questions about that? So this thing really is kind of acting like an inverse of the matrix sigma, right? When I multiply it, by this sigma inverse matrix, I get a square matrix back, right? That has all of its diagonal entries equal to 1. Now, if I multiply them in the reverse order, right, sigma inverse times sigma, I won't get back the identity matrix. The reason for that, right, because it depends on the sizing of the matrices, right? What do I get back if I multiply them in the reverse order? Right, if I multiply sigma inverse times sigma, right, they're compatible that way, right? Because sigma inverse is 4 by 3, and sigma is 3 by 4, right? So if I multiply them in the reverse direction, I should get back a 4 by 4 matrix. What will the diagonal entries of that 4 by 4 matrix be? Right, exactly. Right. So what we'll get back is if you multiply sigma inverse times sigma, right, what you get back is a diagonal matrix, right? 4 by 4 diagonal matrix. The entries are 1, 1, 1, and 0. Right? The last entry will be 0 because it will be the result of taking a 0 column and dotting it with all the rows of sigma inverse. So it's not exactly right. It's not exactly in what you would mean by an inverse, but of course that makes sense because right these are matrices of different sizes, right? A 3 by 4 matrix or can only have rank equal to the largest number of its independent rows or columns, right? So if you have more rows than columns of a matrix, those extra degrees of freedom don't really buy you anything. You can't get more linear independence from a smaller number of vectors. So this is what we end up with. All right, so that's important to keep in mind for some of the discussion we're going to have as we go forward. That this thing sort of acts like it acts kind of like an inverse, but not exactly, right? It's going to be padded with some zeros, depending on the sizes of the matrices. Now, if m is equal to n, right, we get exactly back, a diagonal matrix of all ones, regardless of which direction we multiply. Okay. So using all these observations together, the fact that I is equal to a times vi over sigma I, but we can write that sort of in matrix form. So let's let capital U be the matrix. So let me just clear all the ink here for a second. So let's let capital U be the matrix whose columns are U1 up to U M, or no, UN. There's n of these things. I know UM. It's m by m. Because the u's are in an m-dimensional space. Let's keep a equal to a, and let's let v be the same thing, right? It's the matrix, right, of eigenvectors of A transpose A. Again, V has as its columns, by definition, V will have as its columns the eigenvectors V1 through Vn. So U is an M by M matrix, and V is an N by N matrix because the V's lie in an n-dimensional space and the U's lie in an m-dimensional space. Now, again, right, we made the assumption, right, that that V was, full dimensional, right? So there'll be a little bit of a mismatch, right, between the dimensions of these things, right? So if V was full dimensional, it means that we'll be missing some U's because of the sizing of things, right? The way that we constructed the U's, right, we only construct one for each V. So in the case that A transpose A is full dimensional, it means that N has to be less than or equal to M. So technically what we would have done was only construct one U for every V, like this. What we'll come back and see, right, just like we saw with the sigma and sigma inverse, right, what's happening here is that, when the dimensions are different, we're going to have to pad everything out with an appropriate choice of eigenvectors for U. So we have to extend U we'll extend U to a full basis of m-dimensional space. It's easy to do that because we can just take the remaining eigenvectors of AA transpose will have to correspond to 0 eigenvalues, right? So we just pick any collection of orthonormal vectors that span that space. We'll come back to that in a minute. By construction, though, what we have is if we take the matrix A and multiply it by this matrix V, what we get back is a matrix whose columns are equal to A times V, right? So this A times V, the resulting matrix, has as its columns A times V. If I multiply that by sigma inverse, what I get back is a matrix whose columns look like A times V1. So this thing right here, it looks like a matrix whose columns are A times V1 over sigma 1 times A times V2 over sigma 2, etc. Right? So this is nothing but U, right? By definition, right? That's how we construct the U's, right? This thing was defined to be U1, this thing is U2, etc. Right? So this is just a matrix reformulation of the construction that we just did. Now, again, to make things simple for a second, right? Let's just assume that we only constructed n of these things. So everywhere you see an m, let's assume it's equal to n for a moment, and I'll extend it in a second. Right? So if sigma is an n by n matrix, right? So now sigma inverse literally is the inverse of the matrix sigma. So I can multiply both sides of this expression by sigma to get that U times sigma is equal to A times V. That would be true even in the m by n case, right? Again, what you don't get back the identity matrix, right? You get back a matrix that will multiply some of the entries of this full matrix by 0, right? To delete them, because that's just the way it would work. Right? If m was smaller than n, and if it's larger than n, like the case that we assumed here, the extra 0 entries on the diagonal have no effect. Okay, and then the final step is we use the fact that so here, to go from step 1 to step 2 here, I just multiply by sigma on both sides, and then for the final step of this argument, all I do is multiply both sides. I multiply both sides by V transpose. Again, because V is an orthogonal matrix, V times V transpose is the identity matrix. And so I get that U sigma V transpose has to be equal to A. So really the only subtlety in this argument is sort of tracking, right, what happens with the differences in dimensionality, right, so that the algebra makes sense. So what this tells us is that, at least under the assumption that A transpose A is full rank, that A can be written as a product of matrices U sigma V transpose, where U are the orthonormal eigenvector of A transpose, V is the matrix whose columns are the orthonormal eigenvectors of A transpose A, and sigma are their shared eigenvalues, only the square root of them. It's the square root of the shared eigenvalues of A transpose and A transpose A. Questions about this argument? No questions? Okay, so to really kind of complete the argument and make the most sense of it, like I said, we need to handle the case where we need to really discuss what happens right when when m is not equal to n, right? So as an example, let's suppose that A transpose A is not full rank, right? So it's not positive definite, it's positive semi-definite. Well, then what we do is we construct all the u's in exactly the same way as before. So for any eigenvalue of A transpose A that's non-zero, we define ui to be equal to A times vi or sigma I. Okay. And so in this case, right, we have n is greater than m. So to construct m is greater than n. So to construct the no, I was right the first time. N is greater than n. Right, that's how we end up with the some of the eigenvalues of A transpose A are equal to 0. So for the ones that are not, we define ui like this, and for the remaining ones, so this gives us a collection. Let's say u1 right up to u. I'm going to use it at k here, where k is less than or equal to the rank of the matrix A. It's actually equal to the rank of the matrix A transpose A, right? It's the number of non-zero eigen values of the matrix A transpose A. And what's left, right, we extend this collection of orthonormal eigenvectors to a basis of our m, right, by padding out the extra bits. So anything that's missing here, we'll complete it by extending to an orthonormal basis, right? So we have to. So basically, what we need to do is we need to define one u for everything, right? Until we get up to the dimension, till we get up to m. So we need little m u's, right? If we don't have enough of them, we take the ones that correspond to the non-zero eigenvectors of A, and then we just pad the rest by adding extra orthonormal u's, right, to this collection, right? So these u's will be defined up here, right, and then the rest of them, uk plus 1, uk plus 2, etc., right? These things will just be, your choice is how to pick them, right? Just extend u1 to uk to be a basis of m-dimensional space. So that's it. That's all we do, right? Basically, the same argument I said, previously, right? We have to pad out the u's, potentially the v's, right? If we don't have enough if we don't have enough vectors, right? Because we still have to define these things in order to construct the matrix U. Like I said, we need M of them to make the decomposition work. The only other change is that we keep the diagonal entries of we choose the diagonal entries in the same way, right? So U sigma I is equal to 1 over sigma I if sigma I is not equal to 0, and otherwise sigma I is equal to 0. Right? This is the same kind of thing we did when we were solving when we found the solution to the linear systems, right? When we went to like invert the matrix, it wasn't invertible, right? Because some of the eigenvalues were 0. So we left the 0 eigenvalues as 0, and we inverted everything else. That's how we solved that linear system. So it's the same strategy here. I construct the inverse by inverting everything that's not equal to 0, and I just leave the zeros as it is. If you do this, you can go back through the entire argument that we just did and see that everything again works out. It's just that some things will be 0 padded in places. And we'll lose a little bit of the uniqueness in the construction because now we're able to extend ourselves to an arbitrary completion of the vector space, right? In sort of any way that we want. And somehow it makes sense, right? You know, if A times Vi is equal to 0, right? And there's sort of not a unique way to define the corresponding UI, right? I can't just define it as A times Vi. I have a kind of an arbitrary choice of how I pick the things. Questions about this sort of padding operation? You can always do this. So given a collection of k orthonormal eigenvectors in an n-dimensional space, it's always possible to extend them to a complete basis for the space by adding extra vectors that are linearly independent, but not necessarily orthonormal to the, and then using that like Gram-Schmidt process to turn them into orthonormal vectors. I don't want to go into that so much. Let's, if you've taken linear algebra, you've probably seen that. If you haven't, let's just take it as a theorem that you can extend, any partial collection of linearly independent vectors, right, to a full collection of linearly independent vectors for any, n-dimensional space. Questions? All of this was just a little bit of algebra, right? You can go back through it yourself to check. It's sort of easy to sort of reverse engineer the SVD, right? In some sense. What I mean by that is that if someone gave you the singular value decomposition, you could check that it has to have the properties that we just described. Right? What I mean is, if it is the case that A is equal to U sigma V transpose, right, where U are orthogonal matrices, right, then it must be the case that if I construct A transpose and A transpose A, right, by definition, A transpose is equal to U sigma V transpose times V sigma transpose U transpose. And A transpose A has to be equal to, right, V sigma transpose U transpose, right, times U sigma V transpose. Okay, and then because the U and V are orthogonal, right, this product of matrices right here is just the identity matrix. So what we get back is U sigma transpose U transpose. This thing is equal to V sigma transpose sigma V. So when I take sigma transpose and sigma transpose sigma, right, are the respective this is basically an eigenvalue decomposition for AA transpose and A transpose A. Right? We can just basically see that because this matrix is diagonal, it literally is a diagonal matrix. If sigma is an M by N matrix, then sigma transpose is an N by M matrix. So sigma transpose is an M by M matrix. It's diagonal, and sigma transpose sigma is an N by N matrix that's diagonal. Right? So these two things are a decomposition of the form QDQ transpose. So that's a transpose at the end there for the matrix A. Right? So we can see automatically, right, that if U and V were, if A is equal to U sigma V transpose, then there's a close relationship between basically the eigenvector eigenvalue decomposition of AA transpose and A transpose A and the matrix A. So this is just sort of reverse engineering it. Right? Basically, what we did in the previous argument was just explicitly construct U and V based on the eigenvector eigenvalue decomposition of A transpose A. So that's where the singular value decomposition comes from. It's actually pretty neat that such a thing exists, to be honest. I think that the eigenvector, like I said, I think the eigenvector eigenvalue one is somehow a bit more intuitive. This one is I think a little surprising, honestly, that such a decomposition exists. But it follows basically from the same sort of algebra and the same kind of little algebraic tricks we've seen for working with orthogonal matrices, and in particular the eigenvector eigenvalue decomposition. Questions about this argument? Okay. If there's no questions, then we're going to take the SVD then is given, right? That we can always take any matrix and write it as U sigma V transpose. Let me show you sort of a quick consequence of this that basically extends an argument we've made before. Oh, I guess before I do that, just I think I just proved all these things. Yeah. Okay. So if you remember, I think maybe a week or two ago now, right? We talked about least square solutions to linear systems. So namely, if someone gives you a matrix A and a vector B, if I want to find a solution to the linear system A times X equals B, but I want to find sort of the solution of least norm. But we worked out a solution to this problem, a little bit ago. The solution is given by setting X equal to A transpose Q D plus Q transpose, where D plus here, right, was the diagonal matrix where we kept just the where we inverted just the non-zero entries of the matrix D. So remember that the way this argument worked is we constructed AA transpose. We used its eigenvector eigenvalue decomposition, which was QDQ transpose, and then D plus, like I said, was the inverse of the non-zero entries of the diagonal of D. We can finish up this. We can turn this argument and kind of complete it into sort of a really nice expression for X by noting that A has to be equal to Q sigma V transpose, right? Because in the singular value decomposition, right, we know that there is some orthogonal matrix Q that corresponds to the eigenvectors of AA transpose that gives rise to the first matrix in the singular value decomposition. So if we kind of combine these things, use the fact that A has to be equal to Q sigma V transpose, and AA transpose is equal to Q dQ transpose, what that tells me is that the matrix sigma in this decomposition, it has to basically be the square root of the entries of the matrix D. Right? Again, because the values of AA transpose are equal to the squares of the singular values. Now, it's important that you put everything in the same, you sort of order all the vectors in the same way here to make this argument work. I'll just assume always that you've done that. So then, using the singular value decomposition, I can construct a nicer solution for X. Right? So what we ended up with last time was A transpose Q D plus Q transpose. It's kind of an ugly little expression. We can write it a little bit more nicely using the fact that A is equal to Q sigma V transpose. But plugging that in, A transpose then is equal to Q V sigma Q transpose. Right? So that's using this definition of A and just taking the transpose, right? So applying the singular value decomposition to A, and then just multiplying it in here. Again, Q transpose Q is equal to the identity matrix because the matrix Q is orthogonal. So what I end up with is V sigma D plus times Q transpose B. Again, sigma and D plus, so sigma II is equal to 1, is equal to the square root of DII. And D plus II is either equal to 0 or 1 over the square root, or just 1 over DII. Right? So it's 0 if DII is equal to 0, and it's 1 over DII otherwise. Which means that if you take sigma and multiply it by D plus, right? So sigma times D plus, the ith entry of this matrix is going to look like the square root of DII over DII, right? If DII is greater than 0, and it will be equal to 0 otherwise. Which means that this product is nothing more than just D plus, not D plus, sigma plus by itself, right? Where by definition sigma plus is just equal to 1 over the square root of DII, which is just equal to 1 over the 1 over sigma II. So in general, I'm going to use this little plus when applied to a diagonal matrix to mean you just invert the non-zero diagonal entries of a matrix. Under that definition, we get that the solution to this linear system is V times sigma plus times Q transpose times B. This matrix comes up all the time when solving linear systems of this form. Right? As a result, we kind of give it a special name. We call it the pseudo-inverse, or the Morse-Penrose pseudo-inverse of the matrix A. Before I give you some more details about that, questions about the algebra here? And all I did was use the singular value use the fact that A has a singular value decomposition, and then just multiplied it by the solution that we got. This X solution that we got last time. And so I don't want to go back to the details of solving that thing, right? You can look back, to the previous lectures to see that. But all I did was, what's new here is that I used the singular value decomposition to simplify this to a particular form. Questions? Okay, no questions then. The Morse-Penrose pseudo-inverse, and this is where the plus comes from. That's how it's always denoted. Is the least square solution to a linear system, AX equals B, and it's given by x equal A plus equal to V sigma U V sigma plus U transpose, where U sigma V transpose is the singular value decomposition of the matrix A. So this is a definition here. A plus is defined to be V times sigma plus times U transpose whenever A has singular value decomposition U sigma V transpose. So a couple things to check about this pseudo inverse. If the matrix A is invertible, right? So what that would mean here is that it's a square matrix of full rank. And we can check that A plus is equal to A inverse. The reason for that is that in this case, sigma plus is equal to sigma inverse. Right? If the matrix is square and full rank, the singular values will be remember that the singular values are equal to the square roots of the eigenvalues of AA transpose. In this case, AA transpose and A transpose A will be full rank matrices. So there will be no zero eigenvalues anywhere, in which case sigma will just be equal to sigma inverse. It will literally be the inverse of the matrix sigma. Then the rest of it is just easy to check, right? If sigma is sigma inverse, then U times sigma times V transpose times V times sigma inverse times U transpose, right, is just equal to the identity matrix of the appropriate size. So that is literally the inverse in the case that A is invertible. If it's not, though, right, it's sort of like the inverse just over the range of A, right, over those things that don't get mapped to 0 under the matrix A. Right? This is essentially what happened when we were solving this linear system, right? We basically solved the linear system over the set of vectors, right, that were not sent to 0 under the matrix A. Right? So only things that are in the span of the eigenvectors that eigenvalues are not equal to 0. So this thing is really useful, right? Because what it tells us is, right, if you can compute the singular value decomposition, right, you can solve arbitrary linear systems. Right? You want to find a solution to AX equals B, if there is one, and computing the singular value decomposition will give you the solution to the linear system, right? Just by sort of computing this little pseudo inverse of the diagonal matrix sigma. Because you can basically solve arbitrary linear systems like this, you should suspect that computing the singular values in practice is somewhat expensive, right? Because it's basically equivalent to solving a linear system, more or less. And indeed, that's the case. We won't have time to really talk about that today. Going forward, we'll talk a little bit about how you compute the singular value decomposition, and we won't derive the algorithms or anything. I'll just sort of state the sort of theoretical results. You would never implement the algorithms for finding these things yourself, because they're sort of very highly optimized routines that do it. But we'll come back and talk about that a little bit. It's similar to the computing the eigenvectors and eigenvalues. It's basically the same kind of method in this case. Okay, so there's lots of interesting properties of the pseudo inverse, but they basically all follow from simple algebraic manipulations of the definition. So as an example, one property that will be useful for us is that A times its pseudo inverse times itself is just equal to the matrix A. Right? This would be true, of course, right? If A actually was invertible, it's of course true that A times A inverse times A is equal to A. There's a little bit more to check here, right, with the pseudo inverse, right? Because it's not the case that A plus times A is equal to the identity matrix, right? So there's a little bit of extra work, right, to do here. Right, but it's not so hard. We just use the definition, right? This is A plus, right? And this is A. Again, V transpose V is equal to the identity matrix of the right size. U transpose U is also the identity matrix because they're orthogonal matrices. So what I get from this multiplication is just U times sigma, sigma plus times sigma times V transpose. But again, by sort of the same argument, right? Multiplying these diagonal matrices together, right? The ith entry of this product of matrices, right? It should look like sigma II times 1 over sigma II times sigma II, whenever sigma II is not equal to 0, right? So this thing is equal to sigma II whenever sigma II is not equal to 0. And it's equal to 0 otherwise, which means that the ith entry here is literally equal to sigma II. And so when I product these things up, I get a diagonal matrix that's just equal to sigma. But U times sigma times V transpose, right, is just the singular value decomposition of A, so the algebra works out. So the only little extra headache that one has to deal with, right, with these singular value decompositions versus like general inverses or something is that you might end up with diagonal matrices that have some zeros along the diagonal, right, but that doesn't really matter in most cases, right, because under this pseudo-inverse property, you almost get back the identity matrix, right? It's the identity matrix padded with some zeros, right, depending on how many zero eigenvalues there are. Okay. Questions about this? It's the same sort of, again, it's sort of the same kind of thing we did when we solved the linear system, right? When you computed this almost inverse, right, by inverting everything that's not equal to 0 on the diagonal. And it's the same construction we did for the singular value decomposition. It's sort of just the same argument over and over here. Right? Yeah. But it leads to a lot of nice properties, right? Very similar things, right? It lets us solve linear systems, and this decomposition into orthogonal matrices times the diagonal matrix, right, basically has the same properties as it did in the symmetric case. Other questions about this? So I had an example optimization problem that I want to solve, but it's going to take more than 10 minutes probably. So maybe what I'll do is maybe I'll point out just sort of one other observation about singular value decompositions versus eigen decompositions in the little bit of time we have left. But I want to make sure there aren't any questions about any of this stuff first. At the very least, you can go home and amuse your friends and family by showing them simple ways to solve, find minimum norm solutions to linear systems. That's guaranteed to amuse and delight at parties. Well, let me show you one sort of weird thing that's maybe a little counterintuitive about the singular value decomposition versus eigenvalue decomposition. Yeah, they do. I agree with. I think especially the SVD, right? It feels a little unnatural. I think. So we're going to do an example where we use this stuff. Next time, I don't have enough time to do the example entirely today, so I think I'll save it. I'm going to do an example of an optimization problem where we need to use the pseudo-inverse in a non-trivial way to get a solution. So we'll construct the dual, and we'll see it involves computing pseudo-inverses, and we'll come to that, and uses this whole eigenvector eigenvalue thing to an interesting effect. It's a little non-trivial though, like I said, so I don't necessarily want to start it right now. let's instead, in sort of the remaining like 8 minutes, just think together about sort of a weird kind of special case to kind of understand what's happening. So let's suppose I give you a matrix A, and it's n by n. It's an n by n matrix, and let's just assume that A is symmetric. Because A is symmetric, what this means is that A is equal to A transpose. So what we have from the eigenvalue decomposition is that A has to be equal to Q times D times Q transpose, right, for some orthogonal matrix Q, some diagonal matrix D. Now, if A is just an arbitrary symmetric matrix, there's no guarantee that the entries of D are non-negative numbers, right? They can be positive, negative, or equal to 0. Right? They can be everything because it's just an arbitrary symmetric matrix. It can have an arbitrary set of eigenvectors and eigenvalues. What we just showed, right, is that the eigenvalues eigenvectors of A transpose and the eigenvectors of A transpose A, right, give us the singular value decomposition, right? But A transpose, right, is just equal to A squared, and A transpose A is also equal to the matrix A squared because it's symmetric, which tells me that well, A squared is just equal to Q D squared times Q transpose in both cases. So what this tells me is that A, it seems to tell me, and this is why I want to sort of pull this out as sort of a weird special case. It seems like if I would just use the argument that we just made and say, oh well, the eigenvectors of A transpose, right, have to give me the what sort of left singular, the left orthogonal matrix for the singular value decomposition, and the eigenvectors of A transpose A give me the right singular decomposition, right? It should be the case that I can stick these two things together and get the singular value decomposition. What I want to point out here is, though, one has to be a little careful in this particular case, and the reason is that they have to be compatible in a certain way. So as an example, right, you can't just write A is equal to Q times, so the matrix D squared, right, if I was to construct sigma for this, right, I would take the square root of the entries of D, right, so sigma II, right, is equal to the square root of D squared II, which of course is just equal to DII squared. This is not true. Why? Again, because in general, right, these two things won't be the same, right, unless, right, they'll only be the same if D is a non-negative matrix, right? So the singular value decomposition and the eigen decomposition are only the same for positive semi-definite matrices. So how does this work when you have some negative eigenvalues? Well, it turns out that what is the singular value decomposition in that case? Well, we could choose, for example, the matrix U to be equal to Q. We can pick sigma just as I just defined it, right? Basically the square root of D squared, right? So it's like the absolute values of the entries of D. But for V, we can't choose it to be equal to Q transpose. Instead, VI will be equal to, let's say, UI if lambda I is, or let's say, let's use lambda, if DII is greater than or equal to 0. And otherwise, we'll choose VI to be equal to a negative UI. we have to do this because that's the only way that we'll be able to get basically a negative value in the product. So when you product these things up, anything that looks like the dot product with UI, right, is 1, but now it'll have a negative sign in front of it because of the asymmetry in the way that we've constructed U and V. So I wanted to point this out because I think, if you once you kind of sit down and start going through some of the algebra of these things yourself, you might get confused by this, right? Why aren't the two things the same? The answer is, in general, they aren't, unless the eigenvalues of the matrix A, right, at least in the symmetric case, are all greater than or equal to 0. Otherwise, you can't use you can't just use the separate eigenvector eigenvalue decompositions for A transpose and A transpose A to construct the matrices of interest here. Right. Now, there's not a problem with the construction that we had, right? The problem here was not that it's not with the construction. It's just that I wrote down A transpose and A transpose A and looked at their eigenvector eigenvalue decompositions of them. The point is that the eigenvector eigenvalue decomposition of a matrix is not unique, right? There's different. I can pick there's different choices for the eigenvectors, right? And you have to pick a compatible one for the SVD. So you can't pick an arbitrary U and V that correspond to the orthonormal eigenvectors of A transpose and A transpose A. You have to pick a compatible set of orthonormal eigenvectors. So going back, right, what I mean by that is it's not a problem with the way we did the proof, because in our proof, right, we constructed U by taking it as A times VI for some collection of orthonormal eigenvectors VI. When we do this, right, if A has a negative eigenvalue, we'll see that we get, right, that U. Let's again assume that A was a symmetric matrix, right? And A times VI, right, will just be VI will be an eigenvector of A, but A times VI will have the sign of whatever the eigenvalue is for that corresponding eigenvector VI. And that's why it works out. I just wanted to just point out that little sort of seeming inconsistency in the construction. It's not a problem if you follow the construction as we've described it, right? It is a problem if you try to construct U and V separately. You can't do that. You have to first construct V and then construct U from it, or construct U first and then construct V from it. Okay. It's not arbitrary, right? You really have to pick sort of two compatible orthogonal orthonormal eigenvectors for the respective spaces in order for it to work out. That's the point that I really wanted to make here, right? You can't treat them in isolation. Like, really, the construction insists that they kind of be picked together. Okay. Now, I'm not sure that made any sense, and if it didn't, don't worry about it for now, right? You can always just assume that you can find a U in sigma and V. The only point that you should bear in mind if you didn't really follow that argument is that relationship between U and V and perhaps the eigenvalue decomposition is not immediately clear. You have to be careful, right? They may or may not correspond to the same eigen decomposition you would get for a symmetric matrix. Okay, so that's a good place to stop. Next time, I'll use the singular value decomposition and this pseudo inverse stuff, right, to do an example of duality. In fact, since people, I think, again, aren't, it's this SVD thing's a little mysterious. Maybe what I'll try to do is find a couple different, applications of this stuff to see how we would use it in practice, right? Just to give us some experience with applying it in sort of some non-trivial contexts. After we do that, the next thing we're going to do is show that the SVD actually solves some other least squares problems. Namely, it solves what we'll call rank 1 approximation problems for finding basically the best rank 1 approximation for the matrix, for some matrix under like sort of in a least squares sense. So there's a really close relationship to solving least squares problems and the SVD in general. So we'll see that argument, but we'll do a bunch of different examples first, I think, to sort of build up a little bit of intuition about the SVD, since I think most of us probably have not spent a lot of time working with these kinds of decompositions.